once again, welcome to this seminar. And this first year seminar, we are returning to our chain of seminars. And our speaker is Silva from our lab, and she will talk about SA-OO-VQE. Okay, it looks like an AI robot. Just kidding. And the next seminar will be in April, and maybe we can tell you more details about it later. So I don't want to prolong it. So Silva, the stage is yours. Welcome and enjoy it.
Hello to everybody, and let me welcome you once again to my speech. Today we will delve into the field of quantum chemistry and quantum computing. So let me begin with some kind of motivation of why you as a user would ever need to compute something on a quantum computer. At the beginning, imagine that you are a computational chemist. You sit down in your office and you are ready to make some groundbreaking computations. Your institute either bought you or made available one of dozens chemical softwares, and you are ready to make the calculations. You sit down, you start the calculations, and you run into several problems. One you knew before you even started about is the large demand on accuracy. We are in the field of chemistry, so the accuracy needs to be very good for the results to be worth something. Not like in the field of astrophysics, where several light years or something is still good enough. But you know about this problem before. You chose perfect software for your calculation, and you run into the second problem, high computational cost. You probably do have access to some cluster or supercomputer, but still, you need to gain access to it, and you need to make every node hour, core hour worthwhile. Which is something you have a big problem. You want to parallelize it. And you run into scaling issues. Not all softwares nowadays, especially in chemistry, are made in a way that you can easily parallelize it. But let's say you are lucky. You found a way to make the software run on several nodes. You run the calculations, you wait, and you get error message because your calculations are memory bound. They are heavy in memory. The software generates large output files. Okay, you sit, you are set. You look on the internet and you want to make at least some of the problems disappear, and you have a look. There is something about quantum computing. There will be new quantum computers around Europe. Okay, you want to use it for your chemical calculations. Okay, but do you know how? You can't, for example, take MolPro and run it on quantum computer. And that's something I want to talk with you about today and offer you a way to take your chemical calculations to the quantum level. So for the objectives of the talk, at the beginning, I will go briefly through the fundamental concepts of quantum computing and a bit about quantum chemistry for those who maybe are not exactly in this field. Then I will also, before delving deep into the SA-OO-VQE method, I will describe the basic VQE approach so that you can then see what are the key changes and key concepts of our method and how can that help with your calculations. Of course, you will also learn how to access our software. And throughout my talk, we will have a look at several hands-on exercises, both with SA-OO-VQE and QuizKit. So let's begin. Why do we even need quantum computers? From, let's say, hardware point of view. Current HPC faces many challenges. We are at the limits of Moore's law. It is nowadays practically impossible to increase the clock speed, increase the frequency of your CPUs. We are reaching the very limits of what physics can do. Also, we cannot make the transistor smaller to infinity because that would obviously not work. And also, even if we have good enough hardware, we are also facing the limits and logical difficulties in multi-level parallelization. Because nowadays, if you want to run something efficiently, you have to be expert in your field and also know HPC very well. And of course, as we are trying to solve larger and larger problems, we are running into computationally demanding applications. Now, and this is where the quantum computing comes into play. Today, we are somewhere in the field of quantum readiness. We do have working machinery. We have accessible quantum computers. We will try to access one of them later in this talk also. But we are not quite right in the field of quantum advantage. Quantum advantage would allow us and will allow us several fantastic things. First, we will get super linear speedup, meaning that the quantum computers will allow us to run the calculations faster than the classical ones. Also, there is inherent quantum parallelism in how the basic unit of quantum computing, qubit, is constructed. With quantum computing, entanglement and superpositions also come into play. This all allows us to scale our calculations with respect to the memory. And of course, with any new kind of hardware, we will get specialized algorithms that will allow for new approaches to the standard problems. As I mentioned, the basic unit of quantum information and what you will be working with if you decide to delve into quantum computing is quantum bit, oftentimes called qubit. For qubit, we are interested in ground and excited state of the particle. But also, there are possible extensions to qubits or qubits where we are working with more basic states. If we have a look for basic qubit, we can see that generally it can be written as a linear combination of two basis states, ket0 and ket1. These two states, for what we need, make up something we call a computational basis. And if we have a look at the Bloch sphere, which is one of the ways we can graphically describe the quantum state, we can see that ket0 and ket1 are on the opposite poles of the sphere. Also, you may be interested, is there only one time of qubit? No. There is quite a lot of research already done and much more being developed, but already we have different types of qubits: superconducting, trapped ion, even topological qubits, photonic qubits. There are machines working with quantum dots. We also have spin qubits, neural atom qubits, and qubits based on a superfluid. Now, how do we affect the qubit? You know, classical bit, it's either 1 or 0. But in the quantum field, it is a bit different. We are working with something we call quantum gates. These gates represent unitary operators, and we can think of them as of matrices. These gates are applied or realized to qubits via lasers or microwaves, most commonly. Now, here you can see the overview of the basic gates. Some of them are for one qubit acting on a single quantum bit. And we have also multi-qubit gates that we can work with. You can think of this as our building blocks of the algorithms. Now, okay, we have qubits, we have quantum bits. How do we work with them? We create something called quantum circuit. It is basically combinations of qubits to which we apply several different quantum gates. Here in the example, you can see that at the beginning, each qubit is initialized to ket 0, the ground state, which allows us to know what we are starting with. Then we apply several qubit gates. For example, the H gate is so-called Hadamard gate that allows us to make superposition of the qubit. And mathematically, we can apply the gates, meaning we multiply using the Kronecker product, the matrices, and we can evolve our quantum state. But of course, with every new technology, there are some problems. For quantum computing, we can say in one word, it is noise. As we are working with small systems, it is quite prominent. There are two main types of noise that annoy us. The first one is so-called sampling noise. Because by the law of quantum mechanics, if we make a measurement on a quantum state, it collapses during the measurement into one of the basic states. Meaning, if we want to approximate our true results of the quantum circuit, we have to make several, even thousands measurements. And this is where the statistics come into play. So even if we have totally noiseless machine, or in today we have some simulator, and if we want to really simulate the measurements, we have to work with sampling noise. Or at least we have to try to mitigate it or take it into account. The second thing that comes with building real machines is the decoherence. You need to realize that we are basically computing mostly on the states of atoms. And to be honest, they don't like to stay in one state for very long. And everything can disturb the state. So let's say I have a quantum circuit. It is in the ground state. I put there an X gate, meaning I excite it to ket 1. Okay, it won't stay there for very long. It will take, for example, if there is temperature fluctuation, it will destroy the state. Also, mechanical vibration. That's why the quantum computers need to be stored where there won't any vibrations be getting in the way. You can't, for example, hit the quantum machine if you are angry that it's not calculating fast enough. You will break the results. Then there is a thermal noise, or so-called Brownian motions, or even cosmic rays that disturb your state. Okay, you want to have a big quantum computer with a lot of quantum bits. Great. Now you have to take into account the interaction among qubits themselves, so-called crosstalk. As you cannot isolate each bit, and they will interact between themselves. And also two main types of error: energy relaxation, so-called spin lattice relaxation, If you have a look at working quantum computers, it can sometimes be described as T1 error and dephasing error, spin, relaxation. On the internet, you can see it as T2 error. Now, we have to be able to describe the quantum noise to be able to work with it. How do we imagine that the quantum noise is working? We have our input circuit. We have several gates there, and this is the ideal case. How we work with this in general is that we imagine that after every gate that is applied, we think that there can occur an error. So, in principle, we think that there is something like an error gate that has a different probability for different type of error. So we can see that the quantum noise has a large potential to disrupt our calculations, and we have to work with it in different ways. One of the ways to mitigate the quantum noise is to use so-called hybrid quantum classical algorithms. This is great for now because the quantum machines aren't big enough to mitigate the error solely on themselves. So we want to maximize our computational power, meaning we want to use the quantum device where it will work for us and stick to the classical stuff for now, where it would not give us significant speed up, but would include unnecessary noise. Also, if we mix the quantum and classical parts correctly, we will achieve the speed up we need. And this will allow us to solve the real world problems that would be maybe too complex for classical computers alone, or allow us to test the methods we are developing for quantum computers. And of course, as I mentioned in the beginning, this allows for the noise mitigations where we don't want to be on the quantum device too much, where we don't need it. And it in turn allows us for less noisy results. How can this quantum classical combination look? A classical example is the so-called energy minimalization feedback loop, where we do have the quantum circuits that we use to estimate the energy. This is the part that we measure on the real quantum device. We get the results. The quantum circuit is parameterized, and we used classical optimizer to adjust the parameters. So the optimization is done on classical PC. And with the optimized parameters, we do create new quantum circuit that we use for energy measurement. And we do this until the algorithm converges. Meaning that we use the quantum device where the speed up will happen with the measurement of the energy of the system. And we don't use it for classical optimization, where the current state-of-the-art optimizers are made for classical computers. So now let's have a look at the first hands-on. Here we will try to access a real quantum computer and run your own calculations. So please get to the quantumibm.com/composer and let's try to create computational basis. Let's try to create quantum state that has the amplitudes shown here. I will give you a moment and then I will show you the solution. The Quantum Composer by IBM allows us to test simple circuits and run it directly on their quantum computers from the web interface. It is not enough for production calculations, but it is a nice way to see, and there is a bit of a graphical visualization as well, how different gates affect our states, and we can also see the effect of quantum noise. So this is how the quantum composer really looks like. You do have different qubits, and you can simply move the gates onto them. Now, we wanted to create quantum circuit that looks like this or has the amplitudes of the state that look like this. At the beginning, we can see that the amplitude or the expected value here is cat 0, 0. Okay, we need two different amplitudes. We put the first qubit into superposition. Then we want to also affect the second bit, not simply the first one. Meaning we grab 2-qubit gate, the CNOT gate, we put it here. And then we want to do one last thing that is displayed by the red color here. We want to change the phase of the calculation. So we will grab a Z gate and put it here. Okay, this is how you can create a simple quantum circuit. Now, to run this circuit, we are missing one crucial thing, and that is the measurement. Okay, let's add the measurement. Measurement is represented by this. And suddenly, the amplitude changed. Why? Okay, because we are making one simple measurement, and as I said before, when we measure quantum state, it will collapse. Okay. Now, if we want to set up and run this, we click on Setup and Run. We will choose one of the quantum computers available for free and input the number of shots here. When this is all done, you can simply click on Run. And as you can see, my job is running. To see your jobs in this interface, you can click here. And you see your jobs. Now, we can see that our job is currently in progress, meaning it is being offloaded to the quantum device. And it should be ready anytime soon. If not, I can show you the same calculations I ran yesterday in the preparation, that there would be Q on the quantum computer. And you can see that with the real measurements, we have the biggest number of measurements in the two states we were expecting, but we can see also the effect of the quantum noise, as we have something we call parasitical states, meaning that there was quantum error and we collapsed during the measurement into the wrong state. So this was a brief overview of the IBM quantum composer, where you can have a look at different circuits you would like to try. Now, I have several other hands-on prepared. I will go through them here, but for those who want to try on their own, please have a look, maybe even screenshot this slide where I am telling you where to get your hands on these hands-ons and how you can easily run them. All of the hands-ons for today are in the Jupyter Notebook format and are available on my repository. There is also prepared a Conda environment, which will allow you to easily install everything you need to run these calculations. In there, you will install QuizKit and different packages of QuizKit, and also, most importantly, of course, the SA-OO-VQE package. So I do hope you managed to take a photo or screenshot this thing if you want to work on this on your own. And we will move on. Now, the software I will be talking about this whole time is for quantum chemistry calculations. So, of course, I need to make a brief introduction to what is quantum chemistry. It is study of molecular systems. We are using principles of quantum mechanics to try to understand atoms and molecules. Here we can see the molecule of formaldehyde, which is kind of my favorite because this is the default molecule we work on when we want to test something new in our software. Now, let's say that the heart of the quantum mechanics is Schrödinger equation. This is the core equation that allows us to describe how quantum states evolve. The main part is the Hamiltonian, which is a quantum operator that represents the systems. And from that, we can get the total energy of the system, which is really great, by finding the eigenvalues. And of course, the electronic structure calculation is key to predicting molecular properties and reactivity, allowing us to make dynamics calculations or, for example, try to develop new drugs, see how different molecules and atoms will react when put together. Now, let's have a look at the Hamiltonian and the Schrödinger equation. Schrödinger equation is here in the simplest form. Yeah, it looks really nice until you realize that behind each letter is something really crazy. So we have the total energy operator, the Hamiltonian. The Hamiltonian is the operator that represents the total energy, meaning that there is the kinetic part and the potential part. And let's say the thing we want to do, we want to solve this equation to find energy levels, eigenvalues of the Hamiltonian operator, and the wave functions, the states of our molecular system. Now we do have some operator, okay, and how do I put it into quantum circuit? Okay, we do have, of course, a way how to do it. For that, we need to rewrite the molecular Hamiltonian in form of formalism of second quantization. Second quantization is a method that describes particles in quantum systems using operators for creation and annihilation. So here you can see how we can describe the Hamiltonian in the terms of second quantizations. A hat is the creation operator, the same but with the dagger is the annihilation operator. This operator obey anti-commutation relations, as you can see here. Okay, that's really good, but I have a bunch of A's, and how do I put it on quantum computer? I didn't help you very much so far, but I will now. We do have different ways to map the fermionic operator the one we get from the second quantization, and map it to quantum bits. One of the ways to do it is the so-called Jordan-Wigner transformation. It is commonly used method to encode quantum states of fermions for calculations on quantum computer. Here we use a linear encoding of qubits, where each spin orbital is mapped to its own qubit. Is this the only way to map the fermionic operator to qubits? No, it's not. It's not even the best one. We have different mapping available. Here I am highlighting two other, the Bragi-Kitaev mapping and the parity mapping. Each of the mapping has different advantages. Jordan-Wigner is good for development of the software, as you know that each qubit represents one spin orbital. Parity mapping, for example, is great because it uses symmetries, meaning we can achieve lower number of qubits in our quantum systems, but we can't see the mapping so well. And then we also have Bragi-Kitaev transformation. That is great for larger systems, as it also reduces qubit count, and with that the gate complexity of our circuit. And it is quite efficient mapping with logarithmic scaling of qubits. And here I will show you how to get from the molecular Hamiltonian to the operator we can put into our quantum circuit. With the hands-on, there is the mapping Jupyter notebook, and I will now go over this tutorial so you can see how you will get your Hamiltonian to quantum circuit. Well, first thing first, you need to have the Hamiltonian.
I'm sorry, can we zoom it a little bit?
I can certainly try. Is this better? Okay. So, as I said, we need to get our Hamiltonian first. For this, when we are using Qiskit interface, we can choose from different drivers that will produce our Hamiltonian to start with. Here I am basically telling that we want to calculate dihydrogen molecule, and I am also specifying that we will be using STO3G basis set. Here I am simply creating our problem, and from the problem, which is handled by the Psi4 driver, I can extract our Hamiltonian, which gives us a bunch of matrices and numbers. Here I am printing the electronic integral coefficients, the alpha coefficients, which is not even the full Hamiltonian. Now, we want this operator in the second quantization form. For this, we do have a ready function. We simply call, here it is, the second Q-op, and we get our Hamiltonian in second quantization. That's great. Now, what is left is the mapping. Okay. Yeah, just one point before we get to the real mapping. Here in Qiskit, this is simply the electronic Hamiltonian, meaning that if you want to work with nuclear repulsion, you can extract it as shown here. and then later add it to your calculations. And now the mapping itself. We simply create our mapper. In this case, I've chosen the Jordan-Wigner mapper. And we map our Hamiltonian in the second quantization form. And now we can see that finally our Hamiltonian is in the form of different Pauli matrices, which we can represent by quantum gates, meaning that we can easily put this to the quantum circuit. So this is the process of mapping. And as I said before, Jordan-Wigner isn't the most efficient mapper, meaning that it won't reduce your number of qubits very much. If you do not know what exactly should you use or which mapping will be the most beneficial for your problem, in Qiskit you can see and method that will automatically try to detect symmetries and detect the correct subspace that can be used to map your fermionic operator to qubits. Here we can see if I use the method provided by Qiskit, I lower the number of qubits quite a bit. I go from 4 in the previous case to simply 1. Now, what is the best way depends on what you really need to do and how you need to further work with your system. Okay. So I've shown you how to get your Hamiltonian to the quantum systems. Now we will finally get to the moment where we can use all of this. Before I get into our method, I will shortly describe the variational quantum eigensolver. This is one of the main hybrid quantum classical algorithms used today, as it is used to find the ground state energy of the Hamiltonian, classically used in many chemical problems. And here we can see the variational principle, which tells us that the expectation value of Hamiltonian with respect to psi, which is our testing function, is always larger or equal to the energy of ground state, meaning that it's a simple minimization problem. And the goal we want to do is to minimize the energy by adjusting the parameters of the quantum circuit, which works as our test function psi. And here you can again see the loop where we get the expectation value of Hamiltonian. We put it into classical optimizer, which gives us a new set of parameters. From that, we get new energy. Pretty straightforward once you have all the parts. Now the test functions, in chemistry oftentimes called ansatz, is a parameterized quantum circuit, meaning that I do have here quantum gates that change the value here in the example rotation by the axis y based on the parameters I inputted here. This is how we change the test functions for obtaining the expectation value. We have different types of ansatzes we can use. One of the main type of ansatzes to use when working with chemical calculations is the so-called unitary coupled cluster based ansatz. Here, the example you see CSD allows for usage of single and double excitations, meaning if you know what system you want to calculate and what excitations make sense, this is great ansatz for you. Now, if you do not know that, or you are working with minimization, that is not based in chemistry, you will probably want to use hardware-efficient ansatz. This is a universal ansatz that is typically a bit shorter than the UCC-based one. It's good for problems outside of chemistry that allows you many points where the function can change. And you can also repeat these ansatz to get even more points for optimization. Now the cost function. Great, we are optimizing, we need cost function, obviously. In the basic VQE, the cost function represents simply the energy of the trial quantum state with respect to our Hamiltonian. We want to minimize this, simple enough. Great, the energy is measured on a quantum computer or some kind of simulator. Here, I just want to remind you that here we work with the sampling noise if it's simply the simulator, and quantum decoherence can also change our calculations if we are working on a real device. Now, what are the limitations of standard VQE? If it's such a great method, why are we developing something else? Well, the VQE targets the ground state. With the basic variant, you will not be able to calculate the excited states. And also it has problems with near-degenerate systems. Of course, the calculations are also heavily dependent on the choice of ansatz. And the optimization can oftentimes get trapped in local minima. Meaning if we want to calculate the ground state and the excited state, and do so efficiently, we need some different methods. Now, we look at second hands-on, where I will quickly show you how to do the simple VQE optimization on quantum computer based on Qiskit interface. Again, here we are simply creating the quantum operator, the Hamiltonian of the systems. Here, I do have the Hamiltonian. I can represent that as a matrix and use NumPy eigensolver to find the minimal eigenvalue. And for our use case, we will use that as our reference value. Okay, next step, we have the Hamiltonian, we need the ansatz, the test function. Great. Here I am using one of the hardware efficient ansatzes to show you the two local ansatz. And I am also setting the number of iterations for the SPSA optimizer that we will be using. Great. If anyone wants to store the values and later see how the optimization was going, we can also define the callback function. Now, at the beginning, we will work on an estimator that is made for noiseless calculations, meaning that there will only be a sampling noise, as I've specified the number of shots for the calculation. Okay, and now we simply need to grab the VQE from Qiskit, put our stuff in, and compute the minimal energy. We make the calculations and we get the results. Okay, we used amazing VQE, but we do have difference from the reference energy. Why is that? One thing is that I've used a set and low number of iteration for the optimizers, so that can be improved, but this is clear effect of the sampling noise. Meaning that if I would try, for example, to increase the number of shots, I would probably get better energy, as I would mitigate the sampling error in that way. Okay. And now the highlight of my talk, the state-averaged orbital-optimized VQE. This is the method that I'm developing with my colleagues, and it is a variant of the VQE algorithm that has two crucial changes. First, we are working with state-averaged energy, meaning we are computing and finding the energy and the state eigenvector of our system for both the ground and the first excited state. This enhances the accuracy of excited state calculations as we use weights that are equal, meaning that both the ground state and excited state has the same weight, meaning we can expect the same level of accuracy for both of them. The second part is the orbital optimization, where we are refining the orbital configuration of our system, which improves the simulation's precision. We are changing the Hamiltonian itself. We are changing the orbitals in there. So, what is the advantage here? First one, you are calculating ground and excited state at once. You don't have to run multiple calculations. And second, with the formulation of our cost function, the numerical landscape is oftentimes nicer than if we tried to, for example, calculate simply one of the states. Now, how this algorithm works. In the red field, we have the state-averaged VQE. This you can think of as the classical VQE with different cost function, where the cost function is the state-averaged energy. Then we get the optimal states from this part, the red part, and we moved to the black part, the state-averaged orbital optimization. There is another optimization circle where we are working on the molecular orbitals itself and changing the Hamiltonian so that we increase our precision, the precision of our calculation. Okay, as I said, the state-averaged energy, it provides more reliable estimation of the excited states as the weight is the same as in the ground state. Of course, if you are trying to calculate the system where excited states play a big role, you should use this method and not the traditional VQE where you are not calculating the excited state. And the combination of both the energies balances the effect and the overall contribution to the optimization. Now for the orbital optimization. As I said before, we are refining the very molecular orbitals to match the true electronic structure, meaning we try to reduce approximation errors in the energy calculations. And this step enhances the performance in systems where there is strong electron correlation. Here in this chart, you can see how both the state average in black and the ground state and first excited state energy in color evolves based on the number of cycles of SA-OO-VQE. Meaning that in 2 or 3 cycles, we are getting to the line of the chemical accuracy and below that. So we get that in small amount of cycles. Great. There is one catch. After the optimization with the optimizations of the parameters of our ansatz and with the optimization of the orbitals, the eigenvectors we obtain at the end of the optimization, the circuit with the set of parameters, isn't necessary the true eigenvector of the active space Hamiltonian we are working with. For this, we have implemented the final state resolution, which adds only this small circuit, meaning that there is only few additional gates. And we do one final optimization where we optimize this parameter phi This approach conserves the state average energy, and the eigenvectors obtained after the state resolutions are indeed the true active space eigenvectors. And of course, the states remain orthonormal throughout this process. So let me go briefly through the advantages of state-specific VQE. The first one is the simultaneous excited state optimization, leading to improved accuracy through better energy landscape, meaning we don't have to deal with so much of narrow minima or, on the other hand, barren plateaus. And we reduce via the orbital optimization the approximation errors. Now to the package itself. Package is written in Python and is working with the Qiskit software development kit. It allows you to calculate not only energies, but also gradients, non-adiabatic coupling, state overlaps, and more. It is available both via GitLab and PyPI. And if you want to have a look at our JOS paper where the software itself was first introduced. Now, how to access the package? Go to the Git repository or download it via PyPI. The software comes with ready documentation that is accessible on the read the docs. And I just want to warn you that usage of this software requires you to have at least Python 3.12. Now, the most interesting hands-on we will work on today, and that is the hands-on with the SA-OO-VQE software. So at first, we define the estimator, and we will work with 2 states at the beginning. The work on multiple states is currently in progress and will be part of the package in the following weeks or few months. Here comes into play my favorite molecule, the formaldimine, and I've set some interesting geometry for us today. We will work with active space where there will be 2 active orbitals and 2 active electrons, simply for the sake of the simulations running quickly. I also set the charge and multiplicity and also choose the basis calculations. Okay, then using the SA-OO-VQE package, I create our problem, which is a class that describes our molecule, our active space. We get the Hamiltonian from there. Perfect. Then we are working with the initial circuits. Remember, as we are averaging 2 energies, we have 2 different test functions. You can see both of the initial circuits. This is the beginning that makes sure that our calculations are orthonormal throughout, and we will add the real parameterized ansatz after this part. Here we create the ansatz. Again, it is pretty straightforward. We are using GU-CCSD ansatz, setting the number of repetitions, providing the problem class, and choosing our fermionic mapper. Now, here you can see the ansatz that will be added to each of the initial circuits for the optimization. Okay, great. We have the Hamiltonian, we have the ansatzes. We can create the SA-OO-VQE solver. For that, we need to provide it the estimator, initial circuit, ansatz, the problem, and whether or not we want to do the orbital optimization. We have all of that. What we just need is to define our optimizer and calculate our energy. Here in the output, you can see how the state average cycle is followed by the orbital optimization and so on. We go through quite several loops for this example, and we obtain our energies. Now, you don't have to believe that these energies are correct, of course. So that's why I am ready, and we will compare our energies with the Psi4 calculations. I'm setting the same calculations as before, but using Psi4, and if we go down, we can see that these are the errors between the Psi4 and our calculations. The errors are quite good, especially considering that I've put there quite a limit on the optimizer so that the example doesn't run really long. Now you know how to calculate the energy of the ground and excited system using the SA-OO-VQE solver. I just want to remind you that examples are also provided on the GitLab page of the software and also in the documentation. Now, our solver and software doesn't only calculate the energy. We are also able to calculate the orbital gradients, analytical gradients of potential energy surfaces, non-adiabatic couplings, state overlap, and electronics couplings. Now, for all of the calculations, you need to get the energy, but then you can nitpick what you want to calculate, meaning that you do not have to calculate the analytical gradients if you just need the state overlaps and so on. The state overlaps, for example, are also uploaded to the QPU because we are getting them by using the Hadamard test. And now the gradients itself. Here you can see the paper where the methodology is described. But as I said before, we get the gradient of the potential energy surfaces and also the gradients of orbitals, circuits, and the Hessians with respect to either orbitals or circuits or orbitals and circuits. Here you can see the chart where we are comparing these gradients with those obtained by the Molkes software that maybe some of you have already used. Also, we are calculating the non-adiabatic couplings. These facilitate the transitions between electronic states in molecules, and they are quite necessary for dynamical calculations. So we can also calculate this. Now, the new part in the system is the orbital diabatization. Now, if you are a chemist, you know that the diabatization is oftentimes problematic. And if you want to go through that, it is oftentimes quite computationally heavy process. Here we have proposed and submitted article, and the method is already inside our solver. The orbital diabatizations, where we are working with a transformation-free diabatization and ab initio approach, meaning we try to maximize overlap of the electronic states across geometries, leading to the diabatic results. And here is the comparison between in blue the adiabatic calculations and in orange and yellow with the adiabatic. If we have a look at, for example, the 2.5 degrees at the top in the middle, we can see that with the diabatic calculations, we correctly find the conical intersections between the ground and excited states. But with the adiabatic approach, we have the so-called avoided crossing. So if you need diabatic calculations, you can also use our software for this. Now, just a short example of how easy you can calculate the gradients once you have the energy. At the beginning, I am running the same calculations as we did with the energy. And now I want to calculate the gradients. I calculate the gradients for each state in this case 2, and for each atom we have 5 atoms in the molecule. And I simply on the solver call eval and gradients, and the gradients are automatically calculated. Meaning if I know I want simply one of the gradients, I don't have to calculate all of them. And as I was also talking about the non-adiabatic coupling, we can calculate them in similar manner. It is quite user-friendly interface. If you know what you want to calculate, you simply do it. And again, you have the choice between which atoms you want the results for and which maybe you do not need exactly right now. In similar way, you can of course calculate other stuff that is available in our software. Now, we are still working on this software package, and there are 4 main ways we try to enhance this toolkit. The first one is the simple development, where we will add derivatives of electronic couplings and implement support of different analytical gradients. And also, which we are currently working on, as I already said, the ability to calculate multiple excited states at once. This you can expect in following weeks. Then, as we are getting ready to running this stuff on a real quantum machine when it is here in Ostrava, we are making a study of the noisy environment. There are calculations of progress. We are trying to find which different optimization methods work the best. And this is all in preparation for the QPM. Although Qiskit allows for some amount of distributed behavior, and we also want to study the GPU simulators and how the GPU offload works with our package. So that is the third way of the research direction. And the one that's in progress right now is the integration to the Quantix software. This will allow us to create quantum dynamics simulations. We are working on the interface and integrating the SA-OO-VQE software as one of the possible solvers in Quantix. And with this, we will be able to seamlessly use SA-OO-VQE in quantum dynamics calculations. If you are interested in Quantix, you can follow the link to the official webpage. At the end, I would like to mention my colleagues who are all working in one way or another on this software. There are people from Ostrava, Italy, and France. And this is all for me. Thank you for your attention.
Thank you, Silvia, for a nice talk. We are now open for questions. And first, I would like to ask online audience to ask questions. So unmute yourself and ask. So there are no questions. So for guys sitting here, do you have any questions? Okay, so I will ask, how have you any idea how let's say developers of well-known quantum computing packages like the using classical computers like Gaussian, MolPro, MolCast, whatever, what are their opinion about your package or Quantix or whenever they would use something like this in their packages or softwares? Or
the Quantix is a well-known package that is developed in Great Britain, and this in itself is used widely and accepted. Our package will be the first one that will allow upload to quantum devices, which is the novelty, as there are different, let's say, backends for and ways to obtain the energies. Now, to be honest, I personally haven't spoken with somebody, with some of the developers of Gaussian, and if they would like to use or implement our software.
yeah, okay. maybe I will have another question if there are nobody else asking. How straightforward is implementation of like more than two electronic states, as you mentioned that you will introduce this in near future, and then connected to this, how it is with your diabatization procedure, how will this be generalized for more than two electronic states?
Okay. So we did quite some study about how to generalize this for multiple excited states. And the results we are obtaining so far is that it is surprisingly straightforward, meaning that it will arrive shortly. And for the diabatizations, as this is the approach our team has come up with, we do have the experts in the field of diabatizations here that and they are sure and already they made quite a progress on how to generalize this stuff.
But is it done already? Are they sure that it will be like just easy to implement, or it will be it is possible?
As far as I know, it is possible. That's
okay.
the state of the stuff now.
Okay, I will ask later some details because I don't want to waste time of anybody here. So, are there any questions? I heard something. Oh, no.
I have a notion for the question, if I may.
Yeah, go on.
Yeah, thank you very much. So just to put on a little detail and let it probably for some more in-depth discussion later, your two questions are surprisingly interconnected. So first of all, yes, we are in contact. I'm Martin Beseda, if you don't see the name of who is speaking, and one of the developers of SA-OO-VQE. So first of all, we are in contact with several co-authors with the other established softwares, namely DIREC, which you mentioned, and the Open Fermion. Mostly in the person, but not only, in the person of Bruno Sanjan, one of collaborators on SA-OO-VQE. Also, we are in contact with several other people like Ayaki Sunaga, who co-develops the DIREC package. So yes, some of them are already using that, not only that they would be interested. And talking about the excited states, it's literally being developed now by two students who are currently doing their PhD under the Institute of Charles Gerhardt in Montpellier. So yes, we are completely sure that it's possible to generalize to the upper excited states, and we already have a theory for that. Currently, the code is being written.
Yeah. Thank you for the input. Okay.
With this, I will end like the discussion. Let's thank Silvia again.
Thank you.
And I would like to announce two upcoming events. The next seminar, quantum computing seminar, will be in April, 10th of April, and Ryszard Kukulski will speak about probabilistic quantum error correction codes with application at NISQ devices. And for those interested in some Qiskit basics and basics into quantum computing, there will be two-day training, or between March 18th and 19th, there will be two-day training about fundamental quantum computation algorithms in Qiskit. So that's it. You should have registration forms in chat if in case that you are interested. And with that, I would like to thank you for attending this seminar and have a nice rest of the day. Bye.